welcome to OpenCV weekly webinar. And today I have with us Jeff Powers, who is the CEO of Arcturus Industries. They make 3D perception software for AR and VR. And today is a very exciting day for them because they are releasing a data set and a competition. And we cannot wait to hear about both of them and also learn how the data set was collected and what is this new pretty novel data set about. Jeff?
Thanks, Satya. I'm excited to talk about that. It's been a big effort from our team working on this overall area for more than a year and cramming to put together this new data set and challenge and being able to launch it today here right on the show.
That's great. And also with us is Phil Nelson, who is the content manager at OpenCV, and he's responsible for putting the show together. Hello, Phil.
Howdy. Thanks for joining us again, everybody. Jeff, Satya, good to see you. If this is your first time joining us, we do a couple things on the show that we do every week. One of those is a special giveaway. At the end of the webinar, we'll be doing a giveaway of an Arcturus t-shirt and a free OpenCV course of your choice. So stay tuned for that. We'll also be doing Q&A from you in the Zoom audience. Please use the Zoom Q&A button at the bottom of the screen to ask your question at any time during the webinar, and we'll do our best to work it into the flow of conversation or save some time at the end to answer the ones we don't get to.
All right. So yeah, let's get started, Jeff. You can put on the slides now, and it's your show.
All right. So here we go. So today we're going to talk about Deep Inertial Prediction, or DIPr, which is our name for a new system that uses IMU data. And if you're not familiar with IMU, I'll talk about that in a second, to keep you tracked and keep you immersed in virtual reality or potentially augmented reality when computer vision fails. So this is what if CV fails? What if the camera data isn't good enough? And that's what we're going to talk about. But before we dive into those details, just a little background on who am I? What is this company? What are we doing? So Arcturus Industries is a team of 17 people. We are a team that was formerly at Occipital, where we worked on things like structure sensor, red laser, and we are now focused on 3D perception for VR and AR exclusively. We're closely partnered with the folks at Valve Software, makers of Steam and Half-Life and the Index headset, at the intersection of VR and computer vision. We do things like tracking of a headset. We do stereo view synthesis, where we can take camera views that are at arbitrary locations and transform them to a viewpoint that we want. We also do things like controller tracking. So if you're playing games, you want to know where your controllers are. So really all the 3D vision that you need to get to do modern VR and AR where everything's based on cameras. Although today we're going to talk about what if the cameras fail. But to set some context, first I'm going to jump right into what is visual inertial tracking for AR and VR. If you've used a VR headset in the last couple of years, it's very likely that that headset had some cameras on it. And those cameras were how the headset tracked itself. The prior solutions before that kind of technology would use base stations in a room or other optical, LEDs and things like that to track fixed objects in the outside world. Like the original Oculus headsets had cameras that you'd say should sit on your desk and they would track LEDs on the headset. But the modern approach is to use cameras that are on the headset and an IMU that's on the headset. And this has the advantage of the thing is completely mobile, right? You don't need to set up your room. The cameras can understand things about the environment, like where are the obstacles, where's the floor, and just automatically set up. And it's lower cost because you don't have all this extra stuff you need to install into your space. So this is kind of the way.
Do you have a headset handy so that people can see?
I do. And for that, I'm going to transport out of I'm actually using Light Twist Beta built by Vikas Reddy, my former co-founder.
Oh, nice.
And so I'm actually not in this beautiful office. I will transport to my real office.
That is so cool.
I'll show you guys. So this is this is a headset that we actually use.
If you stop screen sharing,
Yeah.
we'll be able
Yeah.
to see bigger.
Also, I noticed that you have no junk in the frunk there.
I have no.
Have you ever
junk in the
used?
front.
Have you ever tried any of those like the fans that people are putting in there?
Right.
I haven't, but I've.
So where are the two cameras in this one?
So on this headset, the two cameras are here, but
Yeah.
this headset's kind of special because it has a different tracking system that it normally uses for VR, and the cameras are kind of just a bonus. They allow you to see through to the outside world, and they normally don't provide tracking, but there is an API to get access to the camera data that Valve provides, and anybody can tap into this data if they want to. And so that's precisely what we've done for some of our testing. But it's really nice because we get the combination of this camera data and the headset's own tracking. On another headset, for example, like an Oculus Quest, there's 4 cameras on it, and that's what they use for tracking.
All right. And that's also the reason these cameras are the reason why you don't have to have a cable attached, or you don't have need to have a setup. You just need, you just have this headset and the controllers, right? So that was pretty path-breaking in some sense that, oh, there's no extra thing. It's just these 3 things, 2 controllers and the headset.
That's right. Yeah, self-contained, mobile is crucial for VR adoption, and that's been proven that it can work. And yeah,
so I got a headset this last, November, December, and Oculus Quest. I was shocked what they have put in that device for the price. So, with the discount, with the discount and everything, I got it for $250.
Yeah.
I had not followed this space for quite some time, and I was ready to pay $1,000. I was shocked at the price.
Yeah, the screens in the Quest 2 are just extremely good for how affordable it is. Like, I really can't believe the quality for the price either.
Yeah, it's true. I think part of that is it's probably being sold at a loss, which makes it hard for others to compete. But it has done a great thing for the VR developer community. That's something I really do like, is VR developers, it was really just a passion project until recently, but now you can make real money in VR, which is really exciting.
Right. And so in this talk, whenever we see 2 cameras, usually, in the talk, we will see 2 cameras. These are the cameras that are on the headset. This is the view from the headset. And we will also see some game or something. And in that case, it is the view of the game, what the person is seeing, wearing the headset is seeing inside the VR environment. So just to, in case it is not clear for people who do not have a VR headset, those are the 3 things you will see: 2 cameras from which are looking out, and the view of the gamer who is playing the game.
That's a good clarification. So to continue, I'll beam back into my Light Twist office.
Oh, wow.
See, it needs,
that's impressive.
I got to talk to Vikas about this. There's got to be a sound effect when that happens.
That's
got to go like or something.
So let me just play this little video here, and you can see on the bottom, you can see that camera view, and you can also see inertial signals coming from the built-in gyroscope and accelerometer. So this is the input data that we have for visual inertial tracking, which is really just tracking. And when all goes well, it controls your VR experience. So here we are playing with a little adorable VR dog. And on the left, this is the camera view from the headset. And on the right, this is what the user sees. So the system is tracking, everything is going well, there's no problems. But there can be problems. And so if we watch here we've blinded the cameras. This could happen because you accidentally cover them. The room is dark. You look at an area where there's nothing very trackable. There's a lot of motion blur. And in those moments, you lose track. And so what do you do when that happens? And one of the approaches that makes a lot of sense is to use the inertial sensor, that motion sensor IMU that you have on the headset as well. There's a little IMU built into the headset, and it is able to sense your movement, how you're rotating, how you're translating. There's a problem though with using that data, and that data is noisy, it's biased. These are $1 to $2 sensors. They're not, $1 million IMUs that are on a submarine, right? So when you integrate the data from that sensor it's great for a few seconds and then it can start to fly away. So if we watch here, again, we'll have a situation where we're tracking fine. We blind the headset. And now if you look at this menu on the bottom right, it's flying towards us, but the user is not actually moving. The ground truth versus the predicted position is deviating. Now we're flying far away. This will make the user feel very sick. And you simply can't do this. You can't use pure IMU data for 10, 20 seconds without the risk of this happening. So that's kind of the state of the art that's typically launched out there. But let's take a look instead at our approach, our deep inertial prediction. So
Jeff, can I just interrupt to just summarize very quickly? So what you just said is that for tracking, we need IMU data, right? The gyro and the accelerometer. And then in addition to that, we use visual tracking. You can see those visual features that are overlaid on the camera, on the cameras. And using all of that information, tracking is done. Basically, head tracking is done, right? We know the system knows where we are looking at, and that is why it is able to put menus at certain places, because it knows where we are, where the head is oriented. But if you block the cameras, then that tracking is lost, right? And in fact, the headset would tell you that I'm unable to track, right? It will still let you do whatever you're doing, but essentially tracking is lost. And in that case, we are relying only on the IMU data to keep the track, right? I mean, that visual data is lost. So it's kind of, that's why IMU would do a reasonable job for a few seconds, but then it drifts apart because it doesn't get that visual feedback to correct itself. Is that a good summary?
That's great. Yeah, that's exactly right. The camera data is what keeps us locked in place. It can continue to see the map and knows that it isn't moving with respect to that. The IMU alone doesn't know. So, and that's why we saw the drift on the previous slide. If we had uncovered the camera, we would have snapped back to where we should have been. But you can't always do that. And so you can fall back to this kind of inertial prediction like I showed, which drifts. You can fall back to a pure 3 degree of freedom prediction where you're only determining the user's rotation, which you can do much more longer term. But that will also make the user feel sick if they try to move around, because they're trying to move and they know they're moving, but the pose in the VR system is not moving. And anytime there's that disconnect between what the VR display is doing and what you're doing in your proprioceptive sense, you will feel sick immediately. Like your body will say, this isn't right. And so that leads us to our approach here of deep inertial prediction. I'm going to talk about what this is, but at first I'm just going to show you how it works. So we're going to do basically the same thing. There's another menu. If you look on the bottom right, and you can see how we move with respect to that menu. We're going to blind the cameras, and this time, and we're basically going to stay in the same place. By the way, we mostly blind the cameras here. You can see through a crack, but you'll see that crack is not being visually tracked. So as far as the system is concerned, it's lost track. So here we go. Visual tracking is now lost, and we're now using deep inertial prediction. And we are not flying away. We're not getting closer or farther from that menu. The plot on the top is showing that our position isn't drifting. We uncovered and we're back. So that's deep inertial prediction. It works really well for that sort of scenario. I'll explain ways that it isn't perfect, but it's super promising. So combining deep learning with inertial fusion does lead to some very interesting results. And that's the subject kind of this talk. But also we're going to point to, where the holes are and how this needs to be improved. So how did we get there? First, we had the intuition that we wanted to apply deep learning to this problem because using pure physics wasn't going to solve it. And so we needed to capture some data. And so first we looked at what data sets were out there. Maybe there was data that we could just use. Maybe we didn't need to capture data. If you look at a lot of the data sets out there, a lot of them are focused on use cases like autonomous driving or drones or smartphones. So a couple of years ago, a year and a half ago when we started working on this, there was really nothing available that fit our needs for a headset. and we needed, not only visual data, but inertial data too. There just weren't many data sets. There's been, yeah.
The kind of data set you need for this, do you need a stereo pair plus IMU information, or you just need monocular plus IMU information?
Depending on how you do it, what we need, we want to learn from the inertial data. So we need that IMU data.
Yeah.
And we also kind of need a ground truth. So we also need to know how you moved. So we could use visual data and inertial data and create our own ground truth with tracking. But what if there are track loss moments in the data set? In that case, we need a ground truth. So what we need is motion trajectories that have some kind of a ground truth position, translation, or pose in general, and then preferably IMU data as well. We don't actually need the camera data, although it's kind of bonus.
All right. Yeah.
So we looked, and there wasn't a lot. There's a new data set that came out last year that looks promising, but it's not commercial, so we couldn't use it for our own work. But really nothing we could find, and so that led us to capture some of our own data. And so what we did is we took the Valve Index headset and we played games. So really hard work. But we just told guys, please stop working and play games today. We need more data. So that's what it's like to work at Arcturus, by the way. So you will be sort of guilted into playing games. So we captured over 20 hours of gameplay data and other types of motion while in VR. We get this data predominantly from the Lighthouse tracking system. Lighthouse is a pretty phenomenal tracking system if you set it up well. It can, if base stations are really far away, if you don't have enough base stations, it can have problems. But when you set it up well, it's perhaps the best VR tracking experience that you can get, in a consumer package today. So we recorded, 20 hours of this type of data while playing all sorts of different games. We did initially record all the camera data as well from the headset, the inertial sensor data, and of course this Lighthouse data. And you're seeing on the left is the trajectory, sort of a top-down view of how's the person moving in their space. So this is kind of the input. And from here, we had this raw data. So we had this real raw data, and we started to think about how are we going to use this to train a system. And what's great is we have real motion. We have real user motion, which is the key. I mean, if we don't have real user motion, I don't know if we're going to be able to train much. We have this real user motion inspired by how people actually move in VR. But what we don't have with the real data is a perfect ground truth. Lighthouse is very good, but it's not perfect. And also, it's harder to augment real data. Think about this. Let's say you have an IMU signal. It has noise in it. It already has noise in it. You can't take that noise out very easily. And if you do, you're going to be smoothing the data. You're going to be making it, you're going to be causing other problems. So with real data, it's harder to augment the data. It's harder to change it, slow it down, speed it up, add noise. So we thought, well, what if we used synthetic data? Well, in that case, we can augment it easily. We can have no noise. We can add any noise. We can move it around. We can speed it up, slow it down. And we also have a perfect ground truth, again, because it's simulated. But it's not real motion. It's not what a real user does. And so, maybe just doing some manual animation in 3D, of something moving around isn't going to lead to something we can really learn from. So what we opted to do was combine them. And we took our real motion trajectory, we fit a curve through it, and we were able to then generate synthetic replica that followed the real user motion. If I showed you this simulated trajectory and the real trajectory side by side, you wouldn't be able to tell the difference. They look identical to a user. They're capturing that real human intent, but they're simulated. And so that's kind of what our starting point was. To dive into that a little more, we have this data from this Lighthouse system. It has a particular frequency to it. It's discrete, it's not continuous. We take that data, we fit B-splines. We fit these curves, essentially, is what you need to know. And go from...
One question. So what are these three curves? We are looking at an RGB curve. What are the three curves?
Good question. Those are essentially angles. So those are angles in three DOF rotation.
Got
So
it.
how is the headset rotating? So,
Yeah.
left, right, up, down, roll.
Yeah.
And we
Yaw
have these
pitch,
discrete
yaw pitch roll.
yaw pitch roll, essentially. Yeah.
Okay.
So you have these discrete points where, the Lighthouse system gave us a pose, both in translation and in orientation. And then we took those discrete poses and we fit a curve through them, like a fully differentiable curve, where at every point we can tell you exactly, the curve shape and the curvature, and we can interpolate it essentially we turned it into a vector, right? We went from, pixel to vector essentially.
Mhm.
And in this vector space, we can then sample this data and generate simulated gyroscope and accelerometer data. If we take the first derivative of the rotation, the orientation, we get the gyroscope data. If we take the second derivative of the position data, we get acceleration data. Basic, college or high school, physics class, acceleration, second derivative of position, velocity, first derivative of rotation. So we're able to obtain this error-free data. If someone takes this data and then integrates it using, idealized, IMU integration, you will literally exactly get back the original trajectory, which would not be the case with the original raw data. So this is often a question in the the community is, well, this is a great data set, but how much can I trust it, right? Is it really ground truth? How is the ground truth bad? What if I start making an algorithm that's so good it's exceeding the quality of the ground truth? That can't happen here because it's simulated.
Yep.
So great, we have data. How do we use it? So we looked at some prior art. And in 2019, there was this really interesting paper that came out called Ronin, where they had the intuition that they're going to take a neural network and they're going to take some raw IMU data and they're going to ask the neural network to just look at a chunk, like a 1 second chunk of IMU data, and predict, well, given that 1 second, how did the user move? How did they translate? If you think about it, that's actually kind of a strange question, because unless you know an initial velocity, I'm getting a little bit into the physics, you shouldn't be able to do that. You shouldn't be able to just take acceleration data and determine a displacement. You should have needed an initial velocity to be able to do that. But nevertheless, this approach worked and allowed them to generate a guess for the displacement over time. And the intuition there is that, yes, in theory, you do need that information, but the ways that people move are so regular and so repetitive that you can just look at that history and determine how someone might have displaced. So they take that. Yeah.
Does it mean, that is very surprising to me, right?
Yeah.
You don't need the initial velocity. Now, is it because the way people move, let's say they are moving, if there is a very quick, movement, then you can predict the initial velocity from that quick movement, and because the head is, kind of on the shoulders, it's after a certain point, if you're decelerating, you could say that, okay, you cannot move farther away than this. Is that the kind of intuition, or?
Yeah, I think it is. Yeah, the idea that you couldn't have been, your velocity has to have been constrained within some reasonable range. And if we see you decelerating and stopping, we probably know you went from whatever you were at to zero now. And so we can then almost back infer what your displacement might have been. The simpler systems before this were ones that basically just said, when do we think you've stopped? And then those systems can basically just halt all motion whenever they think you've stopped. And that actually was already a big improvement over just the pure IMU integration, trying to detect halts in motion. And this is kind of the extension of that. Like, can we have a neural network just somehow do better than that? And it worked. And then they followed up with this with another approach to be more resistant to, say, shocks in the IMU data, which was apparently one of the issues with this. But there's a problem for us in this approach, is that one, it's doing this it's having a CNN do this, and then it's just directly integrating the CNN measurements, just directly adding them together. and it's only doing that at a frequency of 20 hertz. And so that doesn't work for VR, obviously. 20 hertz pose would be uncomfortable. And it's furthermore, it's 2D. They're actually only trying to figure out a walking displacement. So while a very interesting idea, it didn't solve our problem. However, there was a very interesting paper that came out the next year, which was called tight-learned inertial odometry, where what they did there is they took the same idea about estimating displacements, but they incorporated that in real time with a filter that's using general normal physics to estimate, the IMU integration. So using the IMU data, integrate forward velocity, position, rotation, and just do this forward integration and do that in real time. We can do that at any rate that we want using the raw IMU data, but then have the neural network feed in essentially a measurement, quote unquote, measurement of the displacement. And there's a special formulation of the filter that we won't get into that allows you to take in a displacement measurement and have that displacement influence all the parameters of the filter. And then the system thus, in the end, estimates velocity, it estimates position, estimates rotation, and it can do that at any rate. It can do that at a kilohertz if you have a kilohertz IMU data. And this approach worked, and it had very similar, if not better, displacements than the prior approach, but it could do so in real time and is much more closer to being applicable to something like VR.
Interesting. A bit of trivia here. The filter that is mentioned here, EKF, extended Kalman filter, was first used, or Kalman filters in general were first used for tracking missiles, where you could not get measurements. You had very noisy measurements. So that was the first application of Kalman filter. And actually, it was not very well understood. Even though it worked, it was not very well understood for a long time, even though it was used. It's one of those funny things in science and math that sometimes you stumble upon good ideas that you don't completely understand, but they work.
Yeah, that's super cool. I did not know that. And sorry for our misspelling of provide here. We'll fix that later. Fix it in post.
Yeah, I'll fix it in post. I'll go ahead. I'll go in there and do some little VFX for you.
So there was some really interesting prior work here, but nothing quite fit what we needed. TLIO got close, but their goal was also this longer term prediction. Can we predict how, say, smart glasses are walking around a space? Longer term sessions, going up and down steps, things like that. And the goal was to estimate the position as accurately as possible. But when we got into this problem, we realized that it was less important per se to get the absolute position right than it was to get the instantaneous movement right. We wanted the user's proprioceptive sense of motion to match what the system was estimating for them, rather than worrying about, ooh, I just realized you should have been 5 centimeters backwards. Let's just go ahead and move you back. The system shouldn't do that, because if it does things like that, you'll feel sick. So we didn't quite see anything that fit. And so we set out to try to invent a new system. We started largely from the same idea of tight-learned inertial odometry. But one of the big changes that we did make is we fed in our initial conditions from SLAM at the exact moment that we lose visual track, which is not really something that was done previously. And so we feed those initial conditions in, but then we actually made quite a few other changes. Firstly, one of the big changes that we made, and I'm not going to go into gory details here, but we have our filter output some of its live state, and we feed that into the input, basically, where in the input, we're taking this IMU data and we're transforming the IMU data from like just raw data that's relative to the IMU sensor itself. We're transforming it into this sort of idealized IMU that's in the world. And this helps the CNN generalize better, essentially. But while doing that, we actually use a bunch of live state from the Kalman filter. What's the strength of gravity? What are the current live estimated biases? So we fed all that information in, which helped. We then feed that into the CNN. And then instead of estimating its displacement, we estimate velocity. So I'm going to talk more about that. And then we have a CNN. And the CNN, we sort of, in respect, for example, to tight-learned inertial odometry, we actually simplified the CNN a little bit. And the big thing that we did is we made it output velocity instead of displacement. And in the end, it speeds up the CNN execution, and the Kalman filter actually ends up being a lot simpler based on this formulation too. So that's our big first innovation here, that regarding using velocity. And again, the idea is you have this inner ear sense, you have these other joint senses that tell you like, oh, I know I just moved forward. And if your internal sense of your motion doesn't reflect what the system is showing you, that's going to make you feel sick. And so that was our intuition, was that, well, that's kind of like your velocity or your acceleration, more so than it is your position. A person can immediately sense that, but if you ask them how many centimeters did you move forward, they don't know. And so that was our intuition, and that if we optimize velocity, we would probably potentially get a better user experience. And subjectively, I would say that has been true. We've seen that to be true. So we adopted a new metric. Instead of trying to get the right position, we try to get the right velocity. But at first, and let me talk a little bit about that metric. It's pretty straightforward. It's basically when we start this inertial prediction, we measure the difference between the real ground truth velocity and what the system is estimating for velocity, what this sort of EKF neural network combination is estimating. It says 3 meters per second, 10 centimeters per second. The real velocity is 5 centimeters per second. There's a delta there. We sum that up on each axis over this period of time of which we're predicting, which is a relatively short period. We assume that you're not going to lose visual track for hours. It's going to be seconds usually. And we sum that up and we get the mean of that. And that's our metric. So yeah, we were excited and we thought, this is great. This is a really smart approach. We're so cool. And then we found out one of the issues with this was the system was drifting really fast, which is not a huge surprise. We're trying to estimate velocity, not displacement. We're trying to figure out how fast are you moving, not exactly how much did you move. And it stands to reason that perhaps doing that, you would end up with a system that maybe got the velocity pretty right, but did drift more, couldn't correct a displacement error.
The small mistakes in the estimated velocity would lead to large drifts because they are accumulating over time.
Exactly.
You multiply it by time. Yeah. Okay.
And we found but kind of, fortunately, we came up with, we found an improvement that actually made a huge improvement to this problem. And that improvement was, instead of using, just the gravity direction that we're estimating currently and the biases on the IMU, and without going into a lot of detail, basically the IMUs are noisy, they have errors in them, and you have to kind of estimate these errors in real time. And prior approaches that we'd seen didn't take that live estimation and feed it back in to the earlier parts of the system. And so we did that. And by estimating, not only the direction of gravity, but the strength of gravity and the the strength of those biases, feeding those into our input, we were able to eliminate drift by 82%, really bringing us back in line, very close to the position-based or displacement-based approach for position, while still, now, improving very substantially on our velocity metric that we care about. So that was kind of a cool breakthrough. What else did we do? So we kind of talked about this whole simulated data thing that we do. And, there's a lot of other groups that are doing stuff like this these days, like, using Grand Theft Auto 5 to generate realistic data and then training a self-driving car to drive based on that. And generally speaking, people are finding that this works really well, sometimes without any real data in some cases, or a very small amount of real data. So we hoped to be able to, similarly benefit. And when we switched to synthetic data without augmentations, we actually did not harm our metrics after using real data. So we were a little bit worried, okay, we're going to switch to simulated and metrics are probably going to fall off a cliff because we're not capturing a whole bunch of things. And actually they didn't. Like the metrics were very, very similar before and after we switched to synthetic. And then we were able to do even better. So now that we had the simulated data, we can more easily augment that data. So we added gyroscope bias errors into our training data. We added accelerometer bias errors, and we found that we could, in general, improve metrics by about 5% by tuning the gyro bias. Excel bias didn't seem to benefit that much. We also were able to add other types of simulated error. IMU scale. So, what if the IMU is supposed to read 1G, but it reads 1.01 Gs? Like that's a scale error. So we added in fake scale errors and fake, rotation errors. What if the Excel and gyro are rotated a little bit with respect to each other? And in total, we were able to improve our velocity metric by a little over 10%, combining those things together. And then, lastly, some of the other stuff we did, we tuned for our use case. We played with the window size. Maybe having a longer history would allow the system to perform better or not. And we tuned those things and found better parameters. Just generally, we tuned it, and then we found some of the shortcomings, some of the ways where it wasn't working well. And we tried to add additional training data to cover those cases. So that was kind of our approach. And in the end, where do we sum up? Well, firstly, we completely eliminate this rapid flyaway problem. So, pure IMU integration, zoom, you fly off to infinity. That doesn't happen, which is amazing. And then we got a 60% improvement in metrics with respect to doing pure IMU integration over these short windows. If I gave you a number over, a 10-minute window, it would be like 99% because the IMU would fly away indefinitely. But
right.
Over this window that we care about, we were able to improve metrics by 60%. That was a 40% improvement on our metrics over the TLIO approach as well. So, we're pretty encouraged by this, and it does create a pretty nice experience, but it's not perfect, and that's partly why we're here. It does lead to imperfect predictions. So here, what I'm showing on the right is in green is the uncertainty that the system is estimating. So the system is not only estimating the velocities, but it's also guessing how confident it is. In some cases, you might imagine that IMU history is just not that informative. And so the system may say, I don't actually know how you're moving. And in other cases, it might be like, oh, I've seen this before. I know how you're moving. And but unfortunately, sometimes that estimation is overconfident or underconfident. And the predictions are not always perfect, and sometimes the predictions are jittery. If you look at the bottom plot, the blue line, which is the CNN predictions, they're much more jumpy than the real ground truth velocities. So it's imperfect. And additionally, we found another interesting problem, which is in most of the time when you're playing a VR game, or doing many tasks for that matter, you're not moving around a lot. People are kind of lazy. They don't want to, constantly be moving. And so it's a good bet to say, if you know nothing else, it's a good bet to guess that the person's not moving, right? How do you think the person's moving? Oh, 0. Oh, right, you're right. Yeah, they're not moving. So you'd be right more than you're wrong by guessing 0 motion. And the CNN kind of learns that. And so when you move slowly, it tends to underestimate how much you're moving. It tends to say, I think you're not moving at all. And so we did these tests where we do a slow motion, maybe left and right or up or down. And the CNN would kind of underestimate how much you moved. And so that's an issue. We tried adding data to address this, but it didn't fully address it. So that's sort of some of the imperfections in this approach. And kind of leads us to why we want to release a data set and engage the community to see if other people can help. So to that end, today we are launching the Deep Inertial Prediction data set and challenge. It is live now. DIPr.ai, DIPr.ai. You can actually go check it out. We'll be rapidly evolving the site probably over the next couple of days as the dust settles, but it's there. There's also a GitHub repo and you can start playing with it right away. What's in there is a publicly available data set under a non-commercial license. There's testing data, so you can test, how the system works. We actually include a pre-trained model. So we include an EKF, we include an evaluation function, and we include training data as well. And what's in there right now so far is 6.5 hours of trajectory data and IMU data. And all the details on what's in there is on our website. And it's really simple to get started. There's instructions on the GitHub page. You can build locally on your machine. You can also use Docker. So here's someone basically just running a Docker command that's building the Docker instance and then running the evaluation in just a couple commands. After you run the evaluation, it gives you metrics down here. Velocity, mean, absolute error, blah, blah, blah. Those are your metrics. And so if you run just out of the box, you're going to get our metrics, our provided solution metrics. If you start making changes, you'll get your metrics. You get these plots, which show you how well are you doing with respect to just pure IMU integration. Hopefully you're beating pure IMU integration. How close are you to ground truth? So that's the package. And even independent of this challenge that we're launching today, we're hopeful that that data is exciting for folks. We're hopeful that people can find other ways to use it. It's totally independent of our challenge. We'll be excited if people cite and use it for papers. We're really excited to see how people use it. And we may release more. We probably will release more data over time once we get a little more feedback from the community. And then there's a challenge. So there's a challenge where you can win real money. We have $5,000 in prizes to folks who are willing to take some of their time and try to actually solve this problem better than us. We'll pay you in USD or crypto. And really all you have to do to win is beat our solution. We decided that you can't just submit our solution and win. You do need to beat it, but that's sort of the minimum bar. And you have until the end of April. If we don't get, that'll pretty much be the deadline unless we get no submissions, in which case we may bump it back. But we hope that we'll get lots of people excited. There will be a leaderboard. You simply sign up at our website and we will send you the training data. You can already immediately test with the GitHub repo now. You can see the submission procedure, the rules. One interesting thing I want to call out is we don't get access to people's solutions. Like we don't want to see solutions. So if you're interested in participating, don't give us your solution. We're going to have a third party run evaluations. If it makes sense to somehow partner together, then we'd love to see your solution, but we need to talk about that first. So we just want this, people can keep their solutions to themselves, share them with a third party to test, and that's it. So, and then we'll post everything on the leaderboard, and we'll evaluate you'll be able to check that every day, and we'll see who wins in April. So
that's very interesting. In Netflix challenge, didn't they say that you have to share the solution with Netflix? I can't remember.
Yeah, I think so. There's different approaches that people use, and a lot of them do say, you need to share your solution with us, which makes sense because folks want to learn from what you did. Yeah. But we sort of feel that it's better to let people, people can keep that to themselves. But if somebody does want to partner with us or something, we love to discuss that, but we should discuss it, separately.
Excellent. I think that's that puts you at a higher plane, higher moral, ethical ground, I would say.
Yeah, exactly. And I can't end without saying thanks to the team who did all the actual hard work here. So Anatoly, who's been working on this for a while to get DIPr to where it is today. Martin, who's been working on this as well for a while. The whole team came together over the last week. We just decided last week we were going to do this today. So this has been a huge effort. And then, of course, to our friends at Valve, who we're working super closely with, and and they've really enabled us to be able to do this as well. So, and also just mention that we're hiring, and Valve is hiring too. So we'd love to hear from folks that are interested in this kind of topic. 3D deep learning, SLAM, and also just really good system software engineering for these kind of systems. So much of what we do is optimization and systems and low level. And, it's a good week if we're working on a new algorithm. Often we're just trying to make things faster. So
That's great.
I'd love to hear from people interested in that as well.
Could you go back one slide? I have one question. So I just wanted people to know that where they can contribute, right? I mean, algorithmically, it doesn't matter how you are actually getting the improvement, right? The improvement could be in the Kalman filter part, or it could be in the CNN part or something else, right? So could you explain a little bit more? You don't care, right? You're going to treat this as a black box. What they do inside is you don't care. If this is the input, you have to beat the output metric.
That's right. And crucial, that's crucial. We're excited about deep learning, but you don't have to just change the deep model. You can change anything else. You can tune the parameters. Frankly, probably if you tune the parameters of the EKF for a couple hours, you'd probably be able to beat our solution.
Right.
But
that should be the baseline, I think. Extensive hyperparameter tuning on all these various pieces, that itself would give you a boost. That would give you a baseline.
Yeah. And and some of our biggest improvements were, the CNN itself, we did some changes, but it wasn't, I'd say we did more system changes to get to where we are now. So there might be just as much fruit to be had in the system change part. Another thing I want to mention is one of our rules is that we don't want folks to add new recorded data. If people want to do their own augmentation on our training data, that's fine. The main reason for that is because we want everybody to be on equal footing, even if you don't have access to the right hardware to record data and things like that. So maybe in the future, we'll open up to people adding new data, but for right now we want, it's hard for us to exactly enforce whether you did that, but just we ask that people don't add any new training data. They just use the provided training data.
It's actually a lot of work to add data, I guess.
Yeah.
So that way you're safe. Let's take some questions.
Yeah. Go ahead and, if you don't mind, unsharing your screen there, Jeff. Yeah.
Let me do that. Yeah, in case anybody wants to reach us, I'm Arcturus Vision or JR Powers for me.
Thanks.
All right, so let me unshare.
Yeah, during the show, I also hooked us up on Twitter, so we're streaming on Twitter as well. Yeah, that's really interesting, exciting. What can you remind us of the date again for the end of this? When
April 30th.
Okay, awesome.
Unless we get 0 submissions, and then maybe it'll be May 30th.
So I like this. I'm going to start off the questions kind of broadly here because I really liked this one. Where would you say, this is a very in-depth kind of subject, but where would you say people should start, Jeff, if they want to get started developing VR stuff in 2022?
VR, kind of the whole VR spectrum, or VR computer vision specifically?
Well, I mean, let's start with one and maybe go over to the other.
Yeah. I guess I'll speak to VR and computer vision since I know the most about that. There's a lot of, the first thing is just try all the systems you can get your hands on. Get an Oculus Quest. It's not very expensive. Play with it. See what its shortcomings are. Look at some of the new work in 3D reconstruction and tracking, and just kind of start digging in at that level. I think one of the things that's going to be really exciting over the next few years is we're going to go from just having these tracking systems to having these systems that, as you look around your room, everything is mapped and understood. All your obstacles are there. Right now, you have to trace out a line on the floor and stuff like that. That doesn't make sense, right? The system needs to just understand everything. So there's a ton of potential there. Obviously, deep learning is a huge part of how that stuff is going to be done. So, finding all the deep learning tutorials. Look at work from labs like TUM in Munich. Matthias Niesner's lab has some really cool stuff on 3D reconstruction and object recognition and CAD retrieval, things like that. So those are all things that I would check. There's also Daniel Kramer's lab is really doing some great stuff in tracking. So take a look at those folks. On the VR development side of things, I give a plug for a Valve's source engine and all the cool stuff that's being done with Half-Life Alyx. I mean, play Half-Life Alyx. It's mind-blowing. You'll see the potential of what VR can be, like sort of a AAA VR title. And then obviously Unity, Unreal, these things are just amazing. So dive into that stuff and get a headset and you kind of can't go wrong.
Yeah, I mean, your eyes may eventually start to hate you, but there's we'll fix that one someday too. Thanks for that. An anonymous attendee would like to know: have you considered game genre specific models? Do you think there may be some value in having a different model for this tracking for a game that's very intense, like say Beat Saber, versus one that's more, kind of 3DOF almost, standing, you're mostly standing in the same place?
That's a super awesome idea. And we have thought about that partially from just the perspective of not necessarily say, which game are you playing, which could be a great input, but saying, what have you been doing recently? Because we haven't lost track. We're not trying to track your entire game session. We're just trying to track when computer vision fails. And if you've been playing Beat Saber for a few minutes, we should be able to sort of tune some parameters almost on the fly to be like, well, you're probably going to keep doing that same thing that you've just been doing. So per user training and, like refining the model live as you're playing are some super interesting things that we'd love to try.
Yeah, I think it's a really interesting idea. Thanks, whoever asked that. They're anonymous on my screen, so I don't know. Anything to add to that, Satya? Any thoughts on?
I was just there was a joke running in my head that some people like to play the Netflix game.
That's true. That's true. Orlando would like to know: do you see use cases for this? Can you talk a little bit about the use cases for this tech outside of the gaming world?
Well, certainly a similar approach can be used for things like smartphone augmented reality, which is sometimes gaming and sometimes other use cases. So similarly there, if a person covers their camera for a few seconds, we could use an approach like this to continue to provide a seamless experience even when that happens. We've thought it's still gaming, but we've thought about, we can use the same model with, just retraining for things like controller tracking. Not just here, we're showing what happens with your head and you lose track, but with controller, we can lose track too. So, and, game specific training may actually make even more sense there too. So those are a couple ideas. Maybe I don't know what's going on in the defense industry, but maybe they can make submarine inertial trackers smarter using deep learning. They're probably already doing that. Going back to the whole missile example, we're not working on that, but let's say, spacecraft that lose track for some reason. I think really anything that ends up having a potential, camera failure, this type of approach could fit in.
Yeah, I think that makes a ton of sense. Let's we're got about 5 minutes left here. Let's do our trivia question, and maybe we'll answer another question after that. So if you've never joined us before, we do a free giveaway to one lucky Zoom viewer. You have to be in the Zoom. Don't answer the trivia question. If you're in the other chats, you're not going to get anything. The way it works is you type your answer to the trivia question that I'm going to ask into the Zoom chat window. The first person that answers it correctly will win an OpenCV course of their choice and an Arcturus t-shirt. Thanks for that, Jeff and Satya, and thanks OpenCV, of course. If you've won recently, say the last 2 months or so, please don't answer. Give other people a chance. I'm talking to you, Partha.
Step down.
I'm talking to you, Partha. So earlier in the presentation, we were talking about lighthouses. The lighthouses used with the Valve's headsets have a variable input rate, but there was a certain figure mentioned. What number of hertz was that input rate?
Oh, that was fast.
They're off. Nobody's got it yet.
Oh, really? Oh, yeah. I read it incorrectly.
Somebody got it.
I don't see. Where is it? Is it Jeff? I think I see Jeff. Is that correct?
Whatever's 200.
Yeah, Jeff Channeler. Jeff, congratulations. Please send me an email to phil@opencv.org, and we will make sure that you get your free stuff.
And I'll clarify that the frequency is variable because it depends on the number of base stations that you have and how the spinning lasers in the base stations hit the headset can actually have a variable update rate. But 200 is pretty typical.
Okay.
One question, I think it would be very useful for people who are going to compete in the competition, participate in the competition, is are there any limitations on the model size you can use or the computational power you can use, those kinds of things? Are there any restrictions on that?
In terms of it being practical, yes, but in terms of it winning this competition, no. No restriction. So if you can use a massive model and make it smarter, have at it.
Okay.
Yeah, I think we got time for maybe one more question here. What sort of impact on frame rate does this have on a commodity system?
The answer is almost none. Our neural network can compute outputs in just a few milliseconds, even without even using GPU acceleration. One of the great things here is, we have an input that's, it's not that huge. It's, we have 6 degrees of freedom, and then we have a window that is 3.6 seconds long at a rate of 100 hertz. So, so that's what 360 by 6. That's a pretty small image, essentially. That's basically an image, and we're using a ResNet, which is typically used on processing images. So it's kind of like you're using a neural net to process this small image. And as such, it actually is pretty fast, at least with the architecture we're using, it's pretty fast. And so the amount of compute needed to do this prediction is very similar, if not less, than the amount of compute needed to process visual tracking. And so it really doesn't impact the total execution time. That said, it's using a lot more compute than you normally use to integrate an IMU signal, but its comparison to the full SLAM system, it's actually right on par. So it doesn't really harm performance at all.
But there is also this other argument, right, that without this, the system is unusable, right? So even if it was taking more computational power compared to the visual SLAM, it is still better because you don't have that option, right?
A working system is preferable to a non-functional system, regardless of the performance impact. Yeah,
that's right. We'd be able to accept more compute as long as we stay within, say, other bounds like thermal and things like that.
Right.
Yeah, of course. I mean, it is on people's face. You got to be kind of, just...
It's like the tracking is great. Your face may melt.
Yeah, no, just get some, just have a layer of safe asbestos between you and the compute module. You'll be fine. I think with that, we're ready. Satya, you want to take us home today?
Thank you so much, Jeff. I really enjoyed the talk, and thank you so much for doing the competition, publishing this data set. We know that a lot of progress in computer vision, machine learning, etc., has been made because people took the time to publish these data sets. So I really appreciate this on behalf of the entire community. Thank you for coming to the show. Also, thank you, the audience, the entire audience. They show up every week. We are really thankful for that. And thanks, Phil, as always. Jeff, any parting words?
No, I'll just echo the same. Thanks everybody for tuning in. Thank you guys for hosting this and letting us do this. It was fun, and I'm really excited to hear from people.
Yeah, it should be a really exciting thing. Don't forget to join us next Thursday. Our guest will be Gerard Espona. We'll be doing a Unity update for OpenCV AI Kit. It should be really interesting visuals there.
That's great. Thank you, everybody. Bye.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision from the experts at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.